Okay, here's the, whoops, where is it? Where's my little laser? There we go. Here's the transfer function. We're going to draw a Bode plot of that by hand. Step one was calculate k to the sub naught, or k sub 0. Let's see, plug in, get rid of this s, plug in 0 for the other s's. I get 1,000 times 0.1, which is 100, divided by 64. 1.56, the log of that times 20 is about 4 dB. It's our case of pump. There is a complex term, so we should calculate its zeta, and it's 0.5, which is big enough we could ignore it in this example. The breakpoints. Well, here we have a 0. This is kind of new in this example. Most of our previous examples, we didn't have anything in the numerator. Here we have a breakpoint at 0.1, breakpoint at 1, and a breakpoint at the square root of 64 or 8. Here's our breakpoints in order. Put them in that first column. Let's see the ends. At minus infinity, you're looking for something at the origin. That's in the denominator to the first power, so that's n equals minus 1. The next breakpoint is a 0.1, and that's a 0. So that's a positive. It's real to the first power. That's a 1 plus 4. Next breakpoint is at 1. That's real to the power 1. So that's a minus 1. It's in the denominator. And this guy is to the power of 1, but it's a quadratic. It's a complex term. So it's an n equals 2. It's in the denominator. So it's a minus 2. So the cumulative ends are going to be minus 1, 0, minus 1 again, minus 3. The gains are 20 times those cumulative. Minus 20, 0, minus 20, and minus 60. And the phases are 90 degrees times those cumulative ends. So K0, K0 was 4 dB. So let's plot K0. 10 to the 0 is where we put it all the time. Come up here, 4 dB, the way I did my scaling. So this is K sub naught, K sub 0. And that first slope was it minus 20? Yeah, minus 20. So this first asymptote is minus 20. Needs to go to K0, at least the dotted line. In this case, the first breakpoint is actually to the left at omega equals 1. It's back here. So we come down minus 20 to there, and then we're flat. Remember, by the Oven table, the next slope was 0. So that goes to the next breakpoint, which was at 1 again. So flat asymptote there. Then we're back to minus 20 from the Oven table. We go out to the next breakpoint, which was at 8. So 8. Go out there, and then finally the last slope was what? Minus 60 or minus 60. Minus 60. So this last asymptote has a slope of minus 60. In the sketch itself, again, you just sort of smooth out those asymptotes. On the phase, it starts at minus 90, stays flat, and then it goes up because of that 0, up to 0. Then it stays flat to the next breakpoint, drops again to minus 90, stays flat to the next breakpoint, drops another 180 down to minus 270. It stays there forever. So here we have an angled asymptote that goes up because it goes up at the rise in the phase. Here's the midpoint at a 0.1 multiplied by 5 or divide by 5. We should go back to here. There's a point, there's a point, draw that straight line. There's a midpoint, factor of 5 each way, another midpoint, factor of 5 each way. And the sketch kind of follows and stays between those angled asymptotes. Here's my hand-drawn version. Here's the MATLAB version. close enough. Okay, one example where we can't ignore the zeta. Here's our transfer function. We have, we have a 0 at the origin. So the minus infinity breakpoint is going to be a plus 1 to the power of 1. That's a new feature in this example. Let's see, the breakpoints at 1, 10, and the square root of 2500, which is 50. Case of naught, ignore this s, divide by 1 times 10 times 2500. It's pretty small, it's minus 88 dB. Zeta is calculated at 0.02. That's pretty small. That's going to be significant. So that'll be a new feature of this example. So let's see, 1, 2, 3 breakpoints plus the 1 at infinity. That's a plus 1. That breakpoint's a minus 1. That breakpoint's a minus 1. This breakpoint's a minus 2. There they are in order. So cumulatively, it will be 1, plus 1, 0, minus 1, minus 3, multiplied by 20 dB per decade for the slope, multiplied by 90 for the phase. There we go. So the phase plot has to range from plus 90 to minus 270. Let's see what all those. So here we have that. Well, let's see. The K naught was 10 to the 0, or omega equals 1. There is K naught at minus 88 dB. So the top of my plot was at minus 80 dB. We put a dot there, and the initial slope was upwards. It was up 20 dB per decade. So this is just a straight line with that slope going through this point. And then it was 0 to the next breakpoint, which was, wait a minute. Yeah, right. Once we hit 1, the slope is 0. Is that what I drew? Yeah, that's right. So it's plus 20 dB per decade. Then at the first breakpoint, which happens to be omega equals 1, it's flat. And it goes to the next breakpoint, which was 10. It goes down minus 20 dB per decade. Next breakpoint. And then it goes down, I think it's 60 dB. Final slope. Ignore this for a second. This is the handling the zeta part. For the most part, we're just sort of smoothing out the asymptotes. But we're going to have the effect of this zeta is going to be at the breakpoint at 50. Where does this thing have an effect? With its associated breakpoint. A lot of my students had trouble with it. Anyway, let's go back to this. So where we got to worry about the zeta is at the breakpoint that goes along with that zeta. I hope you can do the basic asymptotes of the phase by now. It started out at plus 90 because of the S in the numerator, or 0 at the origin in the numerator, and then dropped at that first breakpoint, stayed flat, dropped again. I'm not going to go through the angled asymptotes. So normally you just sort of shoot between those asymptotes. Now let's talk about the zeta, the effect of the zeta. And our zeta was 0.02, pretty darn small. We'll go back to these two graphs. Here, the smallest zeta that it shows us is 0.05. Ours is even smaller than that. And even at 0.05, you get a 20 dB increase at the breakpoint associated with that zeta. And you get a pretty darn sharp transition in phase for a small zeta. It's already pretty sharp at a 0.05. So let's go back. So this little bump up needs to be something more than 20 dB. I've got it a little bit more than 20 dB, kind of a smoothish bump. And I've got this phase transition a little bit sharper than I otherwise would have. So that's the effect. And like I said, a place where my students had trouble was, where do these things go? And they go where the breakpoint associated with that zeta, with that complex term, go. If there's only one, you're only going to have one little bump. If you have two complex terms with small zetas, you're going to have two different bumps, two different breakpoints. Okay, let's see what MATLAB did. And you'll see it was a very sharp bump up. Let's see, looks like only about 20 dB here, or even less. That's what I don't get. It seemed like it should be even sharper. And a pretty sharp phase transition, almost a straight drop. Again, that was a pretty small zeta. I wanted to do at least one example of that. I think I'm going to skip this final example. You can look at it at my webpage. So after this video, we're going to get into how to interpret these Bode plots. So we're done with sketching Bode plots by hand. If you want to know more, go to my website. Plenty of examples and more words on it. If I made any mistakes in the video, they should be correct in the